I'd like to do sort of a short overview of some just initial sort of discrete signal processing type concepts that often show up just to kind of make sure some things are in the right places. So remember that often we're dealing with sinusoids, and so we're often dealing with periodic waveforms, and we're talking about we'll have a periodic waveform that'll be T0. And we'll definitely look at the periodicity. The periodicity of even a more arbitrary waveform gives you things like Fourier series and things of this sort. Well, we're also going to take that periodic waveform and knowing that it has sort of bounded frequencies and often try to sample it, and again, hopefully, within the Nyquist limit, or maybe give ourselves a little extra room in there. We'll talk about a sampled function of being n with t sub s, where t sub s is the sampling period, f sub s is the sampling frequency. Remember that needs to be twice as high as any of the frequencies in the signal to do typical Nyquist sampling. Now there's a couple other reconstruction theorems that are interesting, one of which being is if things are within a given octave, which is a factor of 2 in frequency, I can also do reconstructions there. And there's a couple different ways you can show some interesting different properties there, but this is always something you run into. Now another thing we run into is talking about as a result of this is we're eventually going to get into questions of convolution and convolution both in discrete and continuous time. Typically discrete is a little bit easier to understand, mostly because when you talk about impulse responses, it's easier to understand. But fundamentally what you're doing is you're going to take your signal, and make them up as a group of impulse responses. Now, in practice, you're thinking, okay, hold on. What I really am doing is doing things in step function, sort of continuous version of it. It's kind of the equivalent of having a switch. But in the same sort of thing, discrete, it'll be like all zeros and a 1. But in practice, I really am looking at the derivative of this function of a sort. And in discrete time, that works out very well. It's just single 1 and all zeros. And you think, right, I'm just going to decompose any sort of sampled system with a bunch of amplitudes into all these pieces. And therefore, I can directly sort of convolve, and the whole convolution argument and structure makes complete sense. If I'm dealing with continuous systems, it's a little messier because I'm really now making a continuous system out of a bunch of effectively infinitesimals, so things that are not sort of discrete sort of samples where I've got a countable number of discrete things, but I'm now dealing with an infinite number of infinite things. And so the mathematics get us a little more complicated, but it's effectively the same thing, and it's very important because it allows us to find the solution to any linear system for arbitrary inputs. And so this discrete convolution gives me a lot of options. There is a continuous form of this as well. The other thing is when I start talking about FIR filters, which are finite impulse response filters, typically cases where the impulse response, h of n, is fixed, usually a case where there's no feedback, there's a very explicit frequency response. If I take all the coefficients of that FIR filter, which are now finite, and I simply sort of connect it with e to the j omega hat k, which is basically, if you think about the delay, connected each of the delays. And if you're thinking z transforms, each delay is a z minus 1, and you just simply put an e to the j omega hat for the j for that, and you're good to go. This is a very straightforward summation, but it's extremely important because it allows me to very easily and quickly get FIR frequency responses, and from that, I can then do some really interesting things of saying I have a particular function, a particular transfer function I want to get. I can directly try to go get and make that happen. So these are just some basic concepts, and it's probably worth just sort of getting comfortable with these things if you are doing discrete signal processing, and that'll help tremendously on how you kind of think through some of these ideas.